Okay? So now the question would be, well, what do these reactions look like? So it's not just the name of the reaction, but what do they represent? Okay? So, definitions. Our acid-base, we're only concerned about the transfer of a hydrogen, in particular a hydrogen ion only. Substitution, it's pretty much the same thing as an acid-base, except what are you exchanging? Not hydrogen. Okay? It's a little bit more complex, but you're doing that exchange from one place to another. In elimination, you're removing 2 sigma bonds, and in the process you form 1 pi bond. Okay, so recognizing these patterns can help. Addition is the removal of a pi, resulting in the formation of 2 new sigmas. Okay? And again, this is a beginning to end scale of our reactions, not individual mechanistic steps. Sometimes a mechanistic step will cover all of those, sometimes it won't. And then the radical, my least favorite, it just does weird stuff. Okay? Interesting, weird stuff, but it just does weird stuff. We don't typically talk about the radical reactions very much. They will come back again this semester a little bit, but for the most part we can kind of ignore them. Okay? So when we talk about an acid-base, substitution, elimination, addition, we want to have kind of a core idea of what that reaction looks like. Because when you move through an exam, what you will be seeing is chemical reactions, not a bunch of text. So when you look at a reaction, you want to be able to start to piece out where did those things come from? What do they represent within those reactions? Okay? So in an acid-base reaction, not very nicely labeled up there, that first species acts as what in the course of this reaction? Okay, so there's some good phrasing there. Not just blatantly shouting out an answer, but I heard something about donating something. Well, how would you know it was donating anything? What are you doing to figure out that it donated? So let's take a step back. Where do you see anything about homo or lumo in this? Okay. I'm not saying you're wrong about any of that, but the level of detail you're going into there isn't explicitly stated outright at the beginning. Okay? So depending on the question asked, that may be relevant. Start simple first. What is happening to that first molecule? What does it look most like in the product? Well, it looks most like that one, right? No. Okay, no, good answer. No, it doesn't look like that one. It's missing a lot of pieces. It looks like this one. Well, what changed?
Charge.
So we could reference the charge. Right? That's an important distinction to note. What else changed? It no longer has the hydrogen. So that structure lost a hydrogen. Right? Well, where did the hydrogen go? To the other structure. So our red structure donated a hydrogen. The blue structure accepted a hydrogen. We can then take that English and tie it back to definitions. The red structure is the acid because it donated a proton, and the nitrogen is a base because it accepted a proton. What if I looked at the reverse reaction? The red structure is now a base. Because that's now confusing, we usually add the term conjugate on top of that to make sure we're referencing that as the product side of the equation. So our red one's the conjugate base and the other one is the conjugate acid. Right? Boil it down to the very bare essentials. If you need to layer more information in, do so. Most students will jump to the most difficult aspect of the question first. Don't do that. Okay? Try and work and step your ways up to it. Does that make sense? Same thing should apply for all the other reactions. The other 3 reactions that are listed up here are substitution, elimination, addition. You'll notice that instead of providing specifics like I did for the acid base, we've got some generic symbols shown in there so that we're all on the same page. Lg, leaving group, BASE would be our base. Okay, solvent is our solvent, and you see nucleophile. Okay, so if we know what those pieces are, we can start to recognize patterns within an individual structure that we see. So ideally, a structure is drawn, you go, ooh, that can act as a nucleophile. Okay, that can act as a base. By identifying that simple initial step and actually acknowledging it and admitting it and potentially even writing it down, you now are on a path to be able to predict your reaction. Okay, kind of make sense? So we good? Too bad, we're good. Substitution elimination is a general reaction. Why do we not see any spider diagrams or specifics of reagents? What makes a nucleophile? Electrons. Okay, in particular electrons to give. So we're looking for lone pair electrons. Where do we typically find lone pair electrons? Where can you find lone pair electrons?
Something that's negatively charged.
Okay, we could go with something that's negatively charged. What something? Okay, something that's polar. This is interesting. You guys aren't providing any specifics, like oxygen. Why aren't you telling me oxygen is negatively charged? Why would you not jump all the way out to that as an example? Wouldn't a negatively charged oxygen be a nucleophile? Why do I not write a negatively charged oxygen?
Because the other things can be nucleophiles.
Other atoms, other than oxygen, can be negatively charged. Right? The point of looking at these here is that those definitions are now so broad that if we pinpoint and say this reagent, we'd have to list an infinite amount of reagents. So our substitution and eliminations are intentionally left very open and vague. You have to know what the definitions are. Nucleophiles tend to be negative. Why do they tend to be negative? We go back to Cass's definition. Available electrons. Well, if I have available electrons, I might very well be negative. So if you can recognize the patterns behind these, that can help you move through and come up with predictions. Right? Have you all heard of spider diagrams before? Right? I believe we will fix that right about now. Okay? Giant white space, because what fills it? This. This is known as a spider diagram. We start at the center and we spider outwards. What is happening on each of those spider legs out? A new reaction. So we're picking a central molecule with which to compare all of our reactions. This way we can try and condense a bunch of information into a single piece of information or a single diagram or figure. This can become very difficult to interpret, but it summarizes our reactions very quickly and efficiently. Okay? So when you look at these, when we talk about them, you're responsible for all of them. So maybe a list is more convenient for you because you just want to memorize them. Okay? Maybe we just want to put them up so they look pretty. The spider diagram works. When we talk about them in class, what we're going to start to do is group them. Where do we see similarities between these? Do those similarities hold true for what we would predict for each of those products? For instance, I see H plus there. What makes H3O plus reactive? The extra hydrogen, meaning H3O plus does what? Donates H plus. HX, what does X typically represent? A halogen. Give me a halogen. You had to say fluorine, didn't you? Don't give me fluorine. Chlorine, I'll accept that one. Okay. HCl, what can you tell me about HCl?
Acid.
And in particular, it's a strong acid. What is that supplying? RH plus. All three of those reagents are doing the exact same thing. Okay. Now, instead of memorizing 3 different reagents, I can memorize H plus, something else comes in. Okay. It can help simplify the memorization process by finding patterns within those. Okay. It can also help you acknowledge where there's super important things that you have to memorize because they don't fit the pattern. What is HBr? It's a strong acid. Wasn't our HCl a strong acid? Yeah, so we would predict HBr and HCl, those reactions end in the same product. In the case of HX, X went to the most substituted position. The X in HBr is bromine,
Yeah.
our Br. Where did the Br go? Not to the most substituted position. Why on earth would it all of a sudden change? Look at the rest of the information supplied. The rest of that information is saying something else is going on there. What is that something else, Mo? It's a radical. That radical reaction now changes the dynamics of that reaction. Okay? So I could spend some time to now memorize radical reactions or go back and review them, or I could remember that those pieces, Ror or H nu or light, represent radicals, and they do the opposite of what I want them to do. Okay? I now have a quick way to memorize that without having to get into a whole lot of details behind each of those pieces. Kind of make sense? It doesn't always work. If you go through and look at the rest of them, those reagents kind of vary all over the place, and we start to see all sorts of kind of strange things come out of them. Electrophilic addition reactions are not the most pleasant. There isn't a nice pattern of saying SN1, it always does this. SN2, it always does this. Okay? You get a big kind of mix of things going on. There are patterns within those. That's what the Play Posit video tries to do, is show some of those patterns, and that's one of the things that I'll try and talk about, is looking for the patterns of those mechanisms so that you can help predict what happens at each of those stages without spending the time of memorizing each of them. Kind of make sense? Right. I believe we had a brief discussion about naming things like Markovnikov and anti-Markovnikov, right? How those are awful, I hate them, don't do it. Do it right, all you'll make me do is angry. But that's it. Okay? Do it wrong, then you'll make me sad, and I can yell at you for it. Okay? So if you're going to go through and memorize the terms of like Markovnikov or Hoffman or Grignard or Wittig, the named reactions, they are important. We are acknowledging someone's pretty potentially amazing discovery at that time in history. Okay? But that doesn't necessarily tie back to the chemistry. So it's where do you want to spend your brain power? Kind of, sort of? Okay. As we continue to look at our alkenes, this is really just more electrophilic addition reactions. Okay. We see a whole bunch more reagents come out. Okay. And a whole bunch more crazy, just weird stuff happening. And we can tend to fall in that pattern of just being like, well, I just have to memorize everything. Again, what I'm going to try to do in the class is get you to recognize where there are some overlaps and to simplify some of that memorization process. You don't want to understand why. That is perfectly acceptable. You just may not like listening to me talk and lecture. Right? That's okay. Okay. We have even more. All of these are examples of kind of spider diagrams, some of them more or less complicated depending on how many reactions we're trying to cram into them. All of these have lots of extra information stashed in them. Okay, because we're here, let's go ahead and start with this one. Does anybody notice anything interesting about what is happening in that reaction? Right, we've lost the double bond. Is there anything particularly interesting about how we lost the double bond? Should have been made a little bit more obvious, but. Right, addition of the hydrogen. Right, an extra layer just got added on this, which should have been in there to begin with. What is that extra layer showing? It's showing stereochemistry in the products. Was there a stereocenter in our reactant? No. So if there's a stereochemistry in the products, what does that mean? Something goofy is happening with that mechanism to force stereochemistry to occur. What is that something goofy? It's a syn addition. Okay? The hydrogen was added on the same side of that double bond. Whereas if we switched to, say, something down at the bottom, we switch it up with an alkyne with just H2, what happens? Where did the hydrogens go? Same side, right? So, well, that matches the pattern that we've already seen. What happened with the one below it? We have the opposite result. So if you remember the mechanism of how hydrogen in an addition reaction works, that it adds as a syn addition, it's not two reagents you memorize, it's one. And every time you see hydrogen with platinum, palladium, or really any metal, you know to add the hydrogens on the same side of the double bond. Okay? When does it not happen? Well, you now have an exception that causes a trip up. That trip up is now something worth memorizing. Does that make sense? So try to find the similarities through those. Instead of seeing them as two independent functional groups and now independent reactions, try to find where they're similar and stick to that similarities. Know which?
All right, so the only exception to that is...
What's our exception? When hydrogen adds to a pi bond, what happens?
Well, it can't be the alkyne, so, I mean, because you said platinum or palladium, but down there...
Or metal, and so this is where reagent stuff comes in. What is Lindlar catalyst?
Well, I'm looking at the metal, but sodium, so what's the exception then?
Where do you see an exception? What is different about that blue reaction at the bottom from the other ones?
So
We
it's
can get rid of all that.
So it's the solvent? It's the NH3 then? Then what's the Lindlar?
Is the NH3 different than the rest? Yeah? Okay.
So what's
What
the
else
Lindlar-
is different?
So what's a Lindlar catalyst?
So this gets into your mechanism, or sorry, your unfortunately reagent memorizations. You have H2, in that case with Lindlar's catalyst. What is Lindlar's catalyst?
Yeah.
Okay. There's a variety of different ways you can do it, but it's typically a poisoned catalyst. Okay. Well, we just swapped one word for another. Went from Lindlar catalyst to poisoned catalyst. Keep going. What is your poisoned catalyst? It's a metal, typically palladium or platinum, with poison. Some kind of sulfate or carbonate compound. So you're usually adding something else. Barium sulfate, calcium carbonate. Both of those work as poisons. So when we look through and try and find patterns, one pattern that we could say, we're adding hydrogens in all cases. How is the hydrogen getting added? Well, if your hydrogen source is H2, where did it come from? Or how did it add? The same side. What if it's not H2? It's doing something else. Okay? The rest of the reagents now become a little bit less important to memorize. You don't need the specific details of each of those, but you can recognize the source of the atoms being added. H2, how is that different from a hydrogen source down here? Where's the hydrogen source coming from in the bottom reaction? From NH3. How is the hydrogen from NH3 different from the hydrogen from H2? What it's connected to. NH3, the hydrogen's connected to a nitrogen. What charge do you think that hydrogen's going to be? Positive. H2, what's the hydrogen connected to? Another hydrogen. What's the charge there? Okay. Zero. There is no charge associated with that. The charge of those intermediates can now dictate something about what's happening in that middle step. Somehow or another, you're pulling off a positive hydrogen here. Could you expect that to be a negative hydrogen from NH3? Could that be a negative hydrogen in NH3? No. Why not? Nitrogen's more electronegative. Could we potentially see a negative hydrogen in H2? It's a little bit trickier. We're at a zero state. There isn't really any polarity associated with that. Maybe the catalyst is doing something weird. Okay? But that's coming in neutral. Down here, it's coming in charged. If it's coming in charged, your mechanism changes. That mechanistic change can be enough to trigger to recognize the opposite of your pattern. Okay? It's looking for some type of similarity and trying to then group what you have to memorize. Okay, whoops, skip that for the moment. We'll see that painfully later. So when we look at the basics of our addition reaction, in all of those cases, we're starting with some kind of pi bond, not necessarily an alkene, it could be an alkyne, and we are now adding two new sigma bonds, what I'm calling LB and LA. What are LB and LA? Lewis acid and Lewis base. Why not call them acid and base?
Because we also have Bronsted, and it depends on what we're giving, hydrogens versus electrons.
So there's the question. If we look at that reagent could be HCl. I could label the H as an acid. Could I label the Cl as a base? As just B for base? Comes a little bit weird there. Remember what would we call our acid and base? Those were strictly referenced for Bronsted-Lowry. Absolutely, the A hydrogen is acting as a Bronsted-Lowry acid. Is the chloride acting as a Bronsted-Lowry base? Nope. In the course of the reaction, what's it acting as? You can get a couple answers on this one. What happens in our first step? What's the most reactive thing in HCl? What's that? Okay. We get this option every so often. We think chloride. Okay. Typically after exams, what usually happens, unfortunately? Crying. What is in your tears? Salt. What is in salt? Sodium. Chloride. When you cry after the exam, I know your face may feel like it's burning, but is your face actually melting off? No. Is chloride the dangerous part in HCl? No. It's actually the hydrogen. Okay. Why is the hydrogen reactive? It has a positive charge. The chloride withdrew the electron density. So what do I need to stabilize that positive charge? Electrons. Where do I have electrons? Now I can move to look at everywhere I've got. The most active electrons are going to be the pi bond because those electrons are in p orbitals, which are higher in energy than the sigma type orbitals everywhere else. Those electrons are now the most active. Those electrons can come out and share with the hydrogen, shuttling electrons to the chloride. What did the alkene act as?
I don't know.
You had it. I thought you said it earlier.
A base?
A base. It accepted a hydrogen. What is the result of that simple arrow push? What happened to the pi bond? It's no longer present. What happened to all the sigma bonds? They're still there. Okay. That big long arrow from the pi bond out to the hydrogen, what am I showing is happening? Electrons moving, forming a bond to hydrogen. Okay. Where's that new bond in my structure? Well, it's clearly between the hydrogen and the atom that had the electrons in the alkene. Which atom had the electrons in the alkene? Somewhat of a trick question. They're shared between two atoms. So how do we know which one to do? Okay. My former students should know exactly what to do. Check them both. Okay. If you don't know, accept that you don't know and draw both options. So I'm going to place the hydrogen here, or I'll place the hydrogen there. Would that be the end of the structure? Missing octets? Okay. Where did the electrons come from to make the bond to the hydrogen? Where did the electrons come from to make that bond? From the pi bond. Where were the electrons come from to make the pi bond? From 2 carbons. Of those 2 carbons, which one got the electrons? Just one of them, which means the other one is positive. Just because you said it doesn't mean you said it loud enough for me to accept. Okay? Now when we look at those structures, what should we be thinking about? Which one's more stable? Which one's more likely to form? Why would I want to know that information? Okay. Number one, it could just be, well, which is the product? And the answer to that is clearly that neither is the product. Why is neither the product? They're charged. So if we have a charged structure, we know we have to continue through our mechanism. Okay? Which of those is more likely to form? Why is the top one more likely to form? The carbocation is secondary. Well, why do I care about the carbocation? If we think back to our rules of reactivity, the very first thing you need to evaluate would be charge. Why? That's the most reactive site. So when I look at these two structures, I need to figure out where that charge is located, zero in there, and now make a comparison between those two structures at that site. Why is the top one more stable than the bottom one? Well, what's our comparison? What do we have to do? Size. That was the answer. We need to shout that back. Oh, we should evaluate the size of the atom holding that charge. Well, what is the atom holding that charge in both cases? Carbon. Is there a difference? No. What do we look at next? Electronegativity. What is the atom holding that charge? Carbon. Is there a difference in electronegativity? No. What do we move to next? Resonance. Is there a difference in resonance? No. Is there a difference in inductive effects? No. Is there a hybridization difference? No. They're both sp2 hybridized. Well, that was everything that was on the list. That's right. That was everything that was on the list. Remember I said how that was not all-inclusive? There are other things that you could evaluate, like what it's connected to, the substitution patterns. How is the substitution pattern affecting this? We have 2 carbons versus 1 carbon, where the carbocation is located. How do those affect stability? What is the difference between 2 carbons versus 1 carbon?
2 carbons is strong.
I don't know what stronger means. You need more explanation than just more stable.
So the two carbons are both kind of sharing their electrons a little bit to stabilize that charge.
And I think you may have said it later too. What'd you guys say? 2 carbons has twice the amount of electrons as 1 carbon. What stabilizes a positive charge? electrons. The 2-carbon one is more stable, thereby saying that that intermediate is more likely to form, which then means the chloride can come in and attack at that point. What is the role of the chloride in this reaction? Stabilizes that charge how? What did it do? It shared electrons with the carbon, thereby calling it a nucleophile. Okay? We could also call that, if we wanted to step out and look at our broadest definition, it's a cyclic Lewis base. Can I call the chloride a Bronsted base? At any point, or let's try it this way, what is the definition of a Bronsted base? A proton acceptor. Did the chloride ever accept a proton? No. So calling it a Bronsted base doesn't make sense. Okay? So why not just use nucleophile, electrophile for our definitions for Lewis acid, or at the very beginning, right up at the top? Why didn't I just say electrophile and nucleophile? In our very first example, HCl, what is the H? By definition, an acid, not an electrophile. So we have to use the broader definition for Lewis because that encompasses both types of mechanisms. One mechanistic step is going to be looking at the Lewis acid being specifically a Bronsted-Lowry acid. The other mechanistic type will be looking at an electrophile. Okay? Does that change the dynamics of the reaction? Okay, well, if you go back and look at each of the reagents, or all, well, here, because we can. If we go all the way back and look at those individual reactions, do we see a difference when we switch between Bronsted-Lowry acids versus electrophiles? Where does the non-hydrogen go in our acid steps? The more substituted. Where did the hydrogen go in the not acid step? The opposite, the not substituted. Oh, there's a pattern. Where did the non-hydrogen atom go in the more substituted? Okay. That pattern doesn't hold water. But by looking for that pattern, we can start to recognize those differences and start to work towards memorizing these reagents by looking at the structures and thinking about their functionality, not just the sequence of letters next to a sequence of lines. Kinda, sorta? Yeah? Maybe? Okay. So when we look at our overall electrophilic addition mechanism, okay, or our addition reactions, okay, we've got a pi bond. We will activate that pi bond by reacting it with an acid. Okay? If that is strictly a Bronsted-Lowry acid, that is talked about in chapter 11 of our textbook. Okay? If it is not specifically a Bronsted-Lowry acid, it is instead an electrophile to force this reaction. I'm looking at chapter 12 and arguably chapter 25 with radicals, and chapter 24 actually with 12. Okay? So it's kind of broken up depending on what we're looking at. If we go through and look at acids, right? So in theory now we're warmed up. I'm warmed up. You're staring at me. Makes me nervous. Okay? What happens if we add a strong acid? Give me the name of a strong acid, which I may regret. But thank you for making me not regret that vague suggestion. HBr. Okay. What is the acid, or what is the most reactive thing now in my reaction? Hydrogen. Why did you not say the alkene? Right? This is an addition. Additions involve pi bonds and alkenes. Isn't the pi bond the most reactive? It's even the first thing I drew. HBr is a polar molecule. Why is it polar? Difference in electronegativity. Is there a difference in electronegativity between the carbons and hydrogens in the alkene? No, which means that's not the reactive structure. That's not where my focus should be. My focus should first be with the most reactive structure. And in recognizing that focus, I notice that HBr is reactive because the positively charged hydrogen. Also important, so let's not forget about it, we do have that chloride that you had suggested first. We do have the negative of the bromide as well. But the more reactive of those, that's why I'm trying to show it bigger, is that positive hydrogen. Okay? Why is that important? Well, if it's positively charged, what should I do? Neutralize it. What do I need to neutralize? Electrons. Where are their electrons? Now I can go to the pi bonds. Oh, I've got a structure with a bunch of pi bonds. Let's have the pi bonds react. Which pi bond? Okay. Doesn't matter is true, not detailed enough. The other option that came out there with a little bit more detail was they're equivalent. They're the same. Because I can't tell a difference, it doesn't matter. Okay? So again, acknowledging the why behind it is important. So what happens if I then just pick one? Let's pick the closest one, right? So we don't have to go as far. Where would that hydrogen, I just drew too many carbons. Where would that hydrogen go? Okay. We're now sharing electrons from that pi bond with that hydrogen, which then means we're making a new bond between hydrogen and carbon. Which carbon of the pi bond? Internal, external. Why external?
Internal, more stable.
You're saying internal? Oh, I heard a bunch of stuff, but the internal was more stable came out. Internal is more stable, and yet you're telling me to put the hydrogen on the external?
Sorry?
No, I didn't. So we do have a couple answers we could go with. We could say the electrons are easier to get out of the structure because they're on the outside, yeah.
Because the double bond starts at 1.
Okay.
So it starts at 2. And if you drew it to
The
the second one,
nomenclature is an entirely different beast. Don't start using nomenclature to define how a reaction works.
because that double, it's trying to explain.
No, keep explaining. So here's the first thing I'm going to ask. Did I draw the product? No. So maybe it's a little bit easier to understand what internal is more stable means if we're actually looking at the product. Am I wrong? Does that make sense? Okay. So I'm going to draw exactly what we just discussed. What's wrong with that? Why is that wrong? What extra bond? Hydrogen can't have 4 electrons. Isn't that what my mechanism says, though? That it can have 4 electrons? What have you all internalized that you need to stop internalizing? That first step is wrong. Right? That arrow results in this product. This product you said is invalid. Okay? That is okay to draw an invalid thing. That just means you have to fix your arrows over here. What is wrong with your arrows? Arrows. You've only shown one. You need a second arrow showing the bond breaking between the hydrogen and the bromine. Don't imply anything. Okay? You have to specify that. Okay, so that helps. That cleans that up. So now it's better.
Now bromine is just a radical. Or, I mean, in
It's going to have a negative charge, so it's going to attack the positively charged.
It's now gained electrons, so it has a negative charge. Okay? So you're right, gaining electrons. One of the things that we could go through and do is make sure that when we started this, we had all our electrons shown. By having that bond shift over, it now has 8 electrons around it. If I showed those 8 electrons, that would now be bromide with a negative charge. And for those of you saying, well, this is stupid, I know all this. When it gets to the end of the semester and you're like, I can't figure out why I did this wrong, I'll be like, did you put all your electrons on your bromide? Yeah. No, I didn't. Yeah. Right. Specify those electrons that can help out, and it can minimize that radical issue. Okay. There was another statement that was made, and a weight is a good statement, because you're probably maybe getting at the same point. Whoever said that, somewhere over there. Was that you? Yeah. Okay. Well, now the negative can attack the...
Carbon.
What would a negative attack?
Carbon number 2. Positive.
A negative needs to attack a positive. Excuse me? Is there a positive in that structure? No. Don't imply it. Don't assume that it's just there. There was a positive charge in that structure. It needs to be shown. Once it is shown, now you can evaluate moving forward. You have to wait for me to finish my thought.
No,
Yeah.
I really can't because I'm confused.
Yes.
The bromine, when it's HBr,
Mhm.
the bromine, is that negatively charged or is that neutral? 'Cause
In
when
the
it's
current
HBr
state,
liquids,
you're right.
it's neutral.
Once it takes the electrons, it would become charged. At this current stage, it is neutral-ish.
So.
How do we fix it so that we can see that it's not formally positive and negative?
No, it's not negative at all. It's the HBr.
It's partially positive and partially negative.
So then when the electrons, like, actually, then it becomes more negative.
Yep, there it is. Okay,
Okay, now you can decide.
you're good. So you will notice that I tend to not show the partial charges, and I'll draw the charges immediately on, particularly for something as polar as HBr, if we're going to draw it all the way out. Okay? If you asked me to just draw it, I would probably just draw H+. And then Br- would just show up later on in the reaction. Okay? But those are officially partial charges. By acknowledging that charge separation, you can come up with the predictive power behind this. Now that we have that positive charge, what was the suggestion? Or now we have the product actually shown, what was the suggestion? What negative? Okay. The bromine attacks the positive, and we would get our final answer when we go through to isolate the product in this reaction, and we end up with this as our final answer. Right? Because the bromine attacks the positive. Isn't that the answer? You have a positive charge. What stabilizes a positive charge? Electrons. Where are their electrons? The bromide is a perfectly awesome option to consider as a source of electrons. Where is there another source of electrons? The pi bond. And what I could be drawing instead of a final product would be,
The next step.
it's technically not another step because of that arrow.
Oh, interchangeable.
They're interchangeable. This is 90% of all answers will be resonance. Okay. Both of these are possibilities. Now our bromide could potentially come in and attack the top case. There are lots of chemists that freak out at what I just did, by the way, with multiple arrows in the same drawing. Are you any of those chemists? Okay, then we won't worry about it. You are chemists. I have dubbed thee. And we end up now with two possible products. There's the one in orange that you were like, wait, where did that come from? If we acknowledge first the reactivity of our structures and consider resonance, That can help us see the potential other products that can form. Which brings in a really big question that gets touched on in first semester typically, but not fully addressed until second semester. We're starting with a material that is known as a conjugated diene. That conjugation complicates the reactivity of the molecule because of internal resonance. We don't typically talk about it in first semester because in first semester, what do you want to do? Get out as fast as possible. So we address the basics and then just say, here's the basics. One thing happens. That's it. Just remember the one thing. OChem 2, one thing doesn't happen anymore. You're lucky if you get 2. Okay? So what you need to be considering at each step is moving those arrows and evaluating what does that produce. What does that produce? Do I need to be concerned about resonance? And the answer to that one is almost always yes. Okay? So then the big final answer would be, which answer do I box in as the correct answer? Kind of waiting for confident answers from you guys. What do we got? Because you all said blue, I'm going to say it's orange. What if you said it was orange? I was going to say it was blue. It depends on the conditions of the reaction. Okay? Why does it depend? It's not even a major and minor. It has to do something with stability. The stability of what? The intermediate is important. Right? What else is important? The carbocation is an intermediate. What else is important?
Does it have to do with?
The product. Right? Why would that be different? Well, take a look at your intermediates. Okay, so we got red versus black. Everyone okay with that? Okay. Which one is more stable, red or black? Why is red more stable? Okay. It is a secondary carbocation as opposed to a primary, which says which product is the favored one. The blue one. Oh, you guys did a good job. Okay. I don't care about the intermediate. Look at the product. Which product is more stable? Why is the orange one more stable? It's the more substituted pi bond, which says which is your product. The orange one. Really? Yes. These reactions are running simultaneously and they effectively cross streams. Okay? If we looked at an energy diagram, okay, which we're going to do, I believe, in just a second, when we think about our energy diagram, we need to be thinking about how those intermediates are formed or where they're coming from. And there's 2 parts that are important to our energy diagram. The kinetics, which is that first part of our energy diagram, and the thermodynamics, the part between the reactants and products. Depending on the conditions of your reaction, you can have a reaction that favors a kinetic product, or you can have a reaction that favors a thermodynamic product. Which one do you think is going to form first, a kinetic product or a thermodynamic product? Kinetic, because kinetics is all about activation energy, way to be fancy, yes. Or speed, right? The kinetic product is the first one to form because by definition, kinetics is all about speed. What is thermodynamics all about? Temperature. If I provide enough energy, time becomes irrelevant. That now becomes the product. So how could I pick a system that would allow me to oscillate between those two? What would I need to change potentially? Temperature. If I run a very cold reaction, which product would I expect? The kinetic product. Why would I not expect the thermodynamic? There's not enough energy to actually activate the thermodynamic reaction. If I run a very hot reaction, what happens? I'll still get both, but because the reaction is hot, what happens with the kinetic product? It reverses. Go back and look at all of your reactions from first semester and roughly 90% of them show one type of reaction arrow. The reaction arrow that is singular in direction, from left to right. Second semester is all about reversible reactions. Okay? So when we look at a reaction, it's no longer just I form a product and I'm done. It's I form a product, this could go backwards. Was there another option? Does that other pathway result in a product that is more stable than the previous one? So you have to be thinking of those other pathways. Are there other ways to control this other than temperature? Yes. Okay? That can be the strength of the reagents. Okay? What we're really thinking about is reversibility of a reaction. Okay? When we think about Gen Chem, it's the same concept. First semester, how many reversible reactions did you evaluate in first semester Gen Chem? I don't know. We didn't even talk about reversibility, right? Did you talk about reversibility in second semester? And some people are like, I blacked that out. Okay, that's okay. Okay. What is equilibrium? Define equilibrium. The point at which the rate of the forward reaction equals the rate of the reverse. Meaning, what are you looking at? Reversibility. Second semester Gen Chem is all about equilibrium, okay, which is all about reversible reactions. Guess what second semester OChem is all about? Equilibrium and reversibility of reactions. It shows up in multiple different dynamics. So what we have to be able to do is to think about energy diagrams and decide, are these reactions reversible or not? That can become tricky. That's why we'll address them as they come up. This is the first case with our alkene. Okay. As far as deciding reversibility, you've probably done this already before. What do you think? Is this reaction reversible or not? No. Why not? Okay, I don't know what not equal on both sides mean, and for sake of time, sorry, I'm going to skip over you. I heard another one that's common. Strong acid. So, and I'm going to mock you too for this, I apologize. But this is how it's taught, so it's okay. Okay. You memorized that that one's not a reversible reaction because it's a strong acid. You know that when we say strong, it's irreversible. Okay. What if I did H3O2? I tried to pick one that y'all knew. You should know that one. You want help with that? I can help. It's okay. HC2, H3O2. Acetic acid. Is that one reversible? Yes. Why is that one reversible? Love 152. Why is that one now reversible? Because it's not a strong acid. Yeah, that's pretty much how it's taught. Okay? We do throw in a bunch of numbers that actually get at what's happening there. What are those numbers? The pKa's and the K's, your equilibrium constants. These were experimentally discovered. How could we look at that reaction and decide which way the reaction goes? We could evaluate the acidity of each compound present. If I look at the acidity of HCl, because I only know the pKa and not the Ka, yes, I know I can calculate it. Shh. -7. What is the pKa of water? My students, you should know that. Oh, good. And a couple of not my students knew that one. 15.7. Which one's the stronger acid? HCl. Why? It has a smaller pKa. I'm just making sure because HCl wasn't a strong acid. Just checking. Okay? Smaller pKa means stronger acid, which means when I run this reaction, HCl is going to act as an acid, and H2O will act as a base. Okay? I can flip then to the other side of the equation. Okay? Because I've already established acid and base on the left, I now know conjugate acids and bases on the right. H3O plus is my conjugate acid. Its pKa I've got 1.5 was what's locked in my brain. That doesn't mean it's right. Yeah. Right? What does that mean? When I look at that reaction, I'm now comparing -7 to -1.5. Which way is that reaction going to go? Why is it going to favor the right? Okay, so logarithmic scale, it's a really, really big difference. It's a really big difference the other way, too. Why is HCl not the favored one? Just saying a big difference doesn't help me. What'd you go with?
Is it because it gets more acidic?
It gets what? Careful.
More hydrogen?
Okay? If we think about our happy states, are we at our happiest when we have the most energy and most reactive, or when we're a little bit more chill and relaxed? Everybody's a little bit different, but okay. Most people tend to settle and be happier with their state when they're in a content kind of non-high stress environment. That's why everybody's sad in OChem. Okay? Reactions are doing the same thing. If I gave you a positive charge, what did that positive charge try to do? Cancel, neutralize. If I give you a strong acid, what is that strong acid trying to do? Neutralize. All things push towards neutrality. When we look at this reaction, the higher pKa is more neutral. So when we look at this reaction is going to favor the right-hand side because that is less acidic, not more acidic. How much less acidic? Okay, this gets back to Morgan's point. Well, it's only 5.5 difference, right? But it's a logarithmic scale. It's 10 to the 5.5 difference. That's a substantial difference. H3O plus is much more stable. The reaction only favors the products. What happens when we move to the lower case? pKa of acetic acid is, actually I think it's 4. I'm actually pretty sure it's 4.23. 15.7, which one's the stronger acid? Acetic acid, so I don't need to worry about that one. -1.5. What happens? It actually now heavily favors the reactant side. So having an understanding of the pKa's can allow me to predict the reversibility or even the forwardability of a reaction. As drawn, this reaction is not very likely to occur. So we could use pKa's to evaluate this. Okay? A lot of our reactions aren't acid bases. So how do we evaluate? So how else could we look at this to try and evaluate whether the reaction was going forward or backwards?
I'm still confused on how with HCl.
Yeah, keep talking.
I know that's a strong acid, so it's going to favor the product side, but with the pK values, I'm now confused because I know it's favoring
The lower the pKa, the more acidic.
right,
Which one's a smaller number? -7 or -1.5? -7. It's that stupid negative sign. -7 is a smaller number than -1.5. Which is better for you? A -$1,500 or -$7,000? Which one are you like, yep, I'd rather be in that hole? Yeah. So you could base it off of which one's closer to 0. The -1.5 is a smaller negative, or sorry, a larger negative than the -7. So it makes it less acidic.
So the more preferred side is the higher pKa?
Is the higher pKa. So when we move to the bottom one, which side was more favored? 4.23 or -1.5. 4.23, what happened to our arrow?
So it's more favored, but still partially that way?
We'll still get some partial the other direction. Why? It has to do with some of the differences. Okay, the exact scale behind that difference becomes variable depending on how close those numbers are.
So for the, when does the reaction become reversible, like, is using pKa's, that's not the only way.
So that's the argument. Yay, 152 told us we could do this with pKa's. Are all of our reactions pKa based? No. Okay. In fact, most of our reactions are not pKa based. So what else could we use? When we evaluated HCl as being acidic, okay, did we have to use, or now let's switch it this way, HCl versus acetic acid? How do we know which of those is more acidic? We go, well, pKa's.
Yeah.
That defeats the purpose. The whole point was to ignore the pKa's. How do I know which of these is going to produce products more than the other? Say that again? Okay. Chlorine is more electronegative than carbon.
Say the number of,
Getting towards the right idea but wrong atom. Why are you looking at the stability of chlorine versus carbon? It'll be oxygen, so we're fixing that, but why? Why are you comparing chlorine to oxygen? What is the most reactive thing in both of those equations? The hydrogen. But that's the same in both those equations. Is that going to help you? No. What do you move to next?
the number of hydrogen bonds.
Nope, because it's the same number of hydrogens transferred.
Who's gonna then get the charge? When hydrogen leaves?
What's the remaining charged structure? Chloride versus oxygen. Deciding whether it's carbon or oxygen is misleading from the formula. We'd have to actually look at the structure. If we look at the structure for the bottom one, negative oxygen versus negative chlorine. Okay. Charge is same. So can I use charge to determine which one's more stable? No. So what do I move to? Size. Which is more? Is there a difference in size between chlorine and oxygen? Yes. What is that difference? Chlorine is bigger. Which stabilizes the negative charge better? Chlorine, because it is bigger. Which means chloride is more stable than acetate, which means HCl is the stronger acid. Did we look at pKa's? No. In fact, what did we look at? Those 5 rules that I told you should memorize in that sequence. Why? So you don't memorize pKa's. Okay. Doesn't this have resonance? Doesn't resonance stabilize that negative charge? Yes. Why am I not using resonance to say acetic acid is the stronger acid? It's lower on the list of things I told you. You look at charge, then atom effects first, then you can move to molecule effects. Move through sequentially. There are exceptions, but it holds pretty darn nicely true. Why is this then helpful? If we aren't running acid-base reactions, we're running
Substitution and elimination addition.
totally fair answer, not what I was looking for. Electrophile nucleophiles. Okay. The same rules apply, except in electrophiles nucleophiles, I don't have pKa values because they aren't acids. So I can't apply those. But I can apply the charge rules. And I can still evaluate stability of those individual intermediates by evaluating according to those rules. No need for memorizing of pKa's. Yes?
So on the bottom one, if you added a bunch of acetic acid, could you force it in a forward direction?
I don't want to open that can. You don't want to open it either. Okay, we can talk about that later. Okay? So what does that mean when we look at an energy diagram? Okay? What we just evaluated was looking at the relative stabilities. Well, how is stability plotted on an energy diagram? Which is more stable? Sorry, running out of time. That pineapple or that pineapple? It's not a crocodile, it's pineapple. Why is the bottom one more stable? It's lower in energy. So by evaluating something now and deciding stabilities, based on looking at our drawings, we can depict where they are on our energy diagram. We can then use that information to predict something about this kinetic and thermodynamic nonsense. See? cyclic. It comes back. So let's start. Reactants. How many different reactants are there? Touche. How many different organic reactants are there? One. Okay. How many different intermediates are there? Two. We okay with red? Wrong one. Dang it. Okay. Sorry, this one needs to be red. Red and blue for these. Okay. So let's take a look at the intermediate. Which one's more stable, red or blue? Why is blue more stable? Secondary carbocation. Isn't the pi bond internal? Isn't that more stable than an external? Yes. But first, we evaluate the charge. So we look at the charge first. That's the primary driver for the reactivity there. The blue one is more stable, so I'm going to draw that one a little lower in energy. Then I will draw the red one. Make sense? Both of those I drew higher than the reactant. Why would I draw those higher than the reactant? The reactant's not charged, the intermediates are. Now let's move to the products. Which product is more stable, blue or red?
Red.
Why is red more stable? We look at the most reactive thing in both those structures. There's no charge, so we move to the next available thing, the highest energy electrons, which would be the pi bond. Right? The pi bond in the red is more stable, so it should be drawn lower. Should it be drawn lower or higher than our reactants?
Lower.
Why lower?
Because lower is more stable. Less energy.
It should be lower than blue for our products, but I want to know back to the reactants.
Does the reactant have two pi bonds?
Two pi bonds versus one pi bond. So my final product should actually be lower in energy than my reactants.
Can you explain that one more time, why the red is more stable?
For the products?
Yeah.
For our products, what's the difference in energy between those two? They have the same sigma structure all the way through. The only thing that's different is the pi structure. Which one should I evaluate first, the pi bonds or the sigma bonds when looking at stability? Okay. Which should you evaluate first, the guy running at you with a knife or the guy just waving at you? Probably want to be concerned about the guy with the knife, right? Why?
Because he could kill you.
He's higher in energy, right? The guy that's just sitting there probably isn't going to have any effect. Okay? Don't draw too many parallels with those analogies. Okay? So when we go through and look at this, sigma versus pi, which is higher in energy? Pi. So now I want to evaluate which of those pi bonds is more stable than the other. In the bottom case, that pi bond is internal, which means those electrons are effectively trapped within the structure, which makes that pi bond more stable. Because it is more stable, it is now lower in energy than the other one. Why not with the other one? Which should I evaluate? The guy running at me with a knife or the guy standing behind a wall with a knife? The guy probably running at you directly with a knife. The guy in front of the wall has to get through the wall first, right? What is the pi bond in the previous case? In comparison to the charge, which is more reactive, a charge or an actual bond? The charge becomes more evaluative, so I compare the energy difference between the charges. The red one is a primary carbocation versus the blue one is a secondary. The blue one being secondary is more stable, drawn lower in energy. What becomes interesting about that is that when we go through to draw our energy diagram, I should probably draw this not in the same color for both of those. Is we get a crossover. So when we run this reaction at low temperatures, which intermediate is going to form? The blue one. Why? It has the smallest activation barrier. If the blue intermediate forms, which products do I get? Blue one. Why? Can the blue connect to the red? No. What happens when I increase temperature for this reaction? Which one forms first?
Oh, wait, it's
The thermo.
It is still the blue one. But because I have enough energy, what happens? It reverses. Now the red one can form. Once the red one hits here, why is the red one not reversed but the blue one can? The reverse energy for the red one has a much higher activation barrier. That prevents the red one from reversing.
Even at that higher temperature?
Even at that higher temperature.
So the crossover is that.
So that crossover is the weird part here because we could end up with two products depending on our reaction conditions. That's why this becomes tricky. Nearly everything that you see in first semester, it's one or the other. Okay? Or they're the same. Okay? Second semester, we get a crossover. For those of you wondering when and how often this shows up, this is the first case. Diels alders the second case. Enolates is the third case. Conjugate additions is the fourth case. All of those are scattered throughout this semester. Yay! Okay? For more on kinetics and thermodynamics, there is a play pause it video for that. Okay? So I would highly encourage you to take a look at that.